Welcome. Happy Friday, everyone. Thank you so much for joining us for today's presentation. My name is Kayla. I'm here representing the Acelab team. We have Michael, Peter, and Chris, all from the Dorken team. So thank you again for joining us. Before we get started, I want to show you very quickly where you can learn more a little bit about Acelab and Dorken on our website. So if you are logged into the Acelab, you'll be taken to the home screen. From there, you can navigate to the search bar at the top, type in Dorken, you'll be taken to their brand page. So you can learn a little bit more about where they're located, where they ship to. You've got some contact information here if you'd like to get in touch with someone from their team. We've got a few highlights here, as well as full categories of products. You can click into any of these products, save it to your firm library for future reference or comparison. So we've got a variety of products here for you to explore. And then, of course, at the bottom, we've got some inspiration photos. So I encourage you to check this out when you get the chance. I'll send you all a link in the chat to access this page. And then a couple more notes before I pass it off to Michael. Today, you will receive a poll during the webinar. I encourage you to fill that out with any extra information for the Dorken team. You'll also have a post-event survey, so feel free to share any feedback you have there. And then, of course, we do know today's session is worth an AIA learning unit. So we actually collected all of your AIA numbers upon registration, but if you're concerned that we didn't get your number, I'm going to put a form in the chat as well for you to fill out and ensure that you get your credit for today. So while that is everything, I think. Oh, and one more thing, actually. We are open to taking questions. You'll see at the bottom of your screen a Q&A button. Feel free to drop any questions that you have there throughout the presentation. Towards the end, we'll go through and answer as many as we can. All right, that's everything. Thank you again, and I'll pass it off to you, Michael.
Okay, good afternoon, everyone. My name is Michael Hooper. I'm the Building Science Manager for Dorken Systems. I'm joined by my colleague, Peter Barrett. He's the Marketing Manager for Dorken. Today, we're going to be talking about NFPA 285 and weather resistive barriers and how it has implications in your wall design. This is, of course, an AIA presentation, so credits will be provided. This presentation was put together in consultation with Priest & Associates. They're a consulting firm with expertise in fire testing, and being a manufacturer, we want to make sure that we get the inputs from the consulting community to make sure that it is accurate. So this course is about the use of combustible materials in wall assemblies and how that affects the risk of fire in the built environment. The relationship between the weather barrier and NFPA 285 is often frequently misunderstood. So this is going to discuss what NFPA 285 test standard is, the relevant building code sections, as well as how it impacts the weather resistive barriers, and then how the NFPA tests these wall designs, the various cladding systems, the various installations, and how it all comes together. And obviously, there's a lot of different variations in how these assemblies go together. So oftentimes, engineering evaluations are used as a compliance strategy. So to review what we're going to be covering, first is the basics of NFPA 285, followed by the weather resistive barrier portions of the building code, the basics of the test wall designs, and how the weather resistive barriers are analyzed for engineering evaluations. Okay, so let's start with what is NFPA 285? Well, to explain that, we need to go back a little bit further to the Unified Building Code. This is going back to about the 1970s. During the energy crisis, the the use of plastic insulations became far more prevalent, and there had to be testing done in order to allow for these materials to be used in building assemblies. The test was very large and very expensive. And anytime a component was changed in this assembly, the entire test had to be redone. To simplify things, a gentleman named Jesse Beadle created a 2/3 scale test, which eventually evolved into the NFPA 285. So this test was being used more and more frequently. The code eventually adopted it. And when the International Code Council was initially formed, they passed the responsibility for fire testing off to the National Fire Protection Association, which evolved into this standard. Now, the purpose of this test is to measure the vertical and lateral flame spread in a wall assembly. And this is not just on the surface of it, but also within the wall assembly itself. And this is a requirement of the building code. In order to pass this test, there's several criteria that need to be met. First and foremost, the flames cannot extend beyond 10 feet above the opening in a window. The thermocouples at 10 feet cannot exceed 100 degrees or 1,000 degrees Fahrenheit. The temperature does not exceed 1,000 degrees Fahrenheit within the wall cavity itself. The temperature doesn't exceed 750 Fahrenheit within the combustible wall assembly. The temperature does not exceed 500 Fahrenheit within the second story above the room that has the fire, and that's measured an inch away from the interior wall. And flames are not visibly observed within the second story room at all. So why does it exist? This goes without saying. It's a life safety issue, and a very serious one at that. So when we talk NFPA 285, when do we need it? The short answer is whenever there's any combustible material. It really starts with foam plastic insulation. So any type of construction, type 1 through 4, that has foam plastic insulation, regardless of height, must have NFPA 285 testing. In addition to that, the type of exterior cladding is going to dictate whether the testing is required. These will include exterior insulated finishing systems, metal composite materials, fiber reinforced plastics, high pressure laminates, and also weather resistive barriers in buildings over 40 feet tall. So these are the test criteria. As I mentioned before, this is strictly a pass-fail. So it either does or does not meet the requirement. Anything that fails means the entire assembly does not pass. So, basics of the building code. The International Building Code in 2012 introduced the NFPA to these various assemblies, and where weather resistant barriers were started to be mentioned as part of this testing. The trigger for it was when buildings were over 40 feet tall. And this testing was per NFPA 285. And of course, this is quite restrictive and quite expensive. So with all the pushback in the industry, they did make some changes to the language to accommodate weather resistive barriers in NFPA 285 assemblies. So the changes are, if the water resistive barrier is the only combustible material in the rest of the exterior wall assembly, no additional testing is required. Or if that weather resistive barrier has a peak heat release of 150 kilowatts per meter squared, or total heat release of less than 20 megajoules per meter squared, or an effective heat of combustion of 18 megajoules, as determined by the ASTM E1354 test, as well as a flame and smoke spread limitation of 25 for flame, 450 for smoke, then the 285 test wouldn't be required for that air barrier. So the fixes were really exceptions, but it only worked in non-combustible wall assembly. So there was a limitations to what the exceptions were. So basically, if your weather resistive barrier was covered by brick, concrete, stone, terracotta, etc., it is an acceptable assembly. No additional testing is required. If the cladding doesn't meet this first exception, you can use a weather resistive barrier provided it's low flammability, no other combustible materials, as stated in that exception there. Oops. So in 2018, the reference number changed, but there was really no other change to the building code. So these exceptions stand today. So let's talk about the basics of the test wall designs and the weather resistive barriers. So this is a typical wall. You got sheathing, framing, insulation, floor, fire stops, air gaps. There is a lot of variables to a wall assembly. And within all of these, there's variations, different types of insulations, different type of base walls. You can understand that performing a scale fire test 2 stories tall can be very expensive if it has to be done many, many times. Combinations are in the tens of thousands. So we need to figure out a way to test wall assemblies and then be able to make substitutions to figure out what would be acceptable. So you kind of test to a worst case scenario, and anything that you can do to change that wall, so long as it doesn't make that wall any worse from a fire spread situation, those would be in effect grandfathered in. So let's get into that a little bit. So you have to look at a wall from how it's constructed, and you take a look at a base wall and you're basically going to split it based on interior versus exterior. So in this case, we're talking a steel stud cavity wall, 5/8 gypsum interior. You've got your exterior surface, and you've got thermocouples that will be measuring the exterior surface, midway point between the combustible insulation, as well as all the other thermocouples that are required to measure the overall criteria that we discussed earlier. So this test could be run with 1/2-inch type C gypsum, but experience has shown that those gypsum instances will end up cracking and allow the fire through. So general rule of thumb is always use 5/8 inch type X gypsum for the interior. So if you look at region 2, again, weather resistive barrier over the base wall assembly. And your weather resistive barrier can consist of many different things. It can be a mechanically attached sheet. It can be a fluid applied. It can be self-adhered. Your exterior insulation has a lot of variables as well. It can be combustible ones such as EPS, XPS, graphite impregnated, polystyrene, polyiso, mineral wool. So a lot of variations. You may have a weather resistive barrier over top of the insulation. In the case of open jointed panels, you would have something like that as well. And again, this can be mechanically fastened, fluid applied, self-adhered. You'll have air gaps. Those air gaps can vary. The type of attachment system plays into this as well. The exterior claddings, so the material type, the thickness, the joints, joint spacing, joint location, all these things are factored into establishing a baseline for your test. And you'll see here all the various thermocouples that are placed. So again, you've got one on the exterior, an inch off. You've got one at half the distance in the airspace. You've got another thermocouple within the continuous exterior insulation halfway through. And that's if the insulation is combustible. If it's non-combustible, this thermocouple is not required. You'll have another thermocouple within the steel stud cavity as well in the interior. So there's a lot of data points that are taken into account when this test is performed. So when we talk typical base walls, these are going to be the most common construction types for type 1 to 4 type buildings. Steel stud wall is going to be your highest risk. So you can substitute a CMU wall or a concrete wall in the case of an NFPA judgment on a stud wall. So you can substitute those in without having to retest for those additional base walls. Right. The testing would be based on 3 5/8 inch deep steel stud, minimum 20 gauge metal, spaced at 24 inches on center. So the typical cavity insulations can vary from none at all to non-combustible, your mineral fibers, fiberglass. You can have spray polyurethane foam, cellulose foam, denim. There's all sorts of materials available. A cavity fire stop must be used, and that would be 4 inches of mineral wool at 4 pounds per cubic foot in density at each of the floor lines, and this is to partition the air spaces to prevent the chimney effect. So your typical exterior sheathing is going to be at minimum a 1/2 inch unrated gypsum or 5/8 inch thick fire resistive exterior type gypsum sheathing. You could technically do the test without any exterior sheathing, but the exterior insulation can only really, can burn from both sides in this case, so it's not recommended. So when this test is performed, they have the source of fire is based within the mock window opening, and the idea is this is to replicate a room fire with the fire coming out of that window and up the face of the building. And this is going to test the exterior cladding as well as the entire wall assembly as well. So any air spaces, insulation, weather resistive barrier, anything that's within that assembly is all at risk of burning. So a lot of different variables. We try to create a baseline and then make substitutions from there. So typically in an assembly like this, your exterior cladding is going to have about a 2-inch air gap between the cladding itself and the insulation or the weather resistive barrier. Anything larger than that, and you're really going to get into problems with a chimney effect, that heat rising up and causing basically a failure of the test and the risk of fire spread. So we do limit that air gap. Now, ACM walls, general consensus is they easily melt, they ignite, they spread flame. If you pass with an ACM, fire consultants can write engineering evaluations that any cladding that is less combustible can be substituted without having to perform a full NFPA test. ACM testing is usually connected to polyiso insulation manufacturers who usually conduct their own testing as a worst case scenario. So again, if we can get an assembly to pass in a worst case scenario, any substitution you make of any material that's going to have a lower peak heat release or a lower flame or smoke spread can be substituted without a problem, without having to redo that NFPA 285 test. So let's discuss the various weather resistive barriers that can be used. We've got fluid applied. These can be rolled, troweled, sprayed, and can be made of any number of materials. You have self-adhered, very common in the marketplace. These can be permeable, impermeable, some bituminous, many plastic-based. They can be mechanically fastened. So these can be mechanical fasteners with washers. These can be held on with furring strips. They can be held on in any number of ways. And the whole idea behind these is to improve building performance and durability. This is what's going to limit air infiltration and exfiltration. It's going to conserve energy. It's going to resist water infiltration while oftentimes allowing water vapor to escape the building and dry out and maintain that building durability. So it's key that we incorporate these aspects into the assembly, but whenever you introduce components, you introduce complexity. With that complexity comes the risk of things like fire propagation. So, as I said, there's a lot of variables in the type of insulation we use, and it can be also used in multiple places. It can be used in the wall cavity itself, as well as continuous exterior insulation. These installations will typically be either mineral fiber insulation, which is a great non-combustible type insulation, but can also be polyiso, spray polyurethane foam, EPS, XPS, GPS. And all of those installations are combustible. So they need to be paired with weather resistive barriers that have been tested or analyzed. The maximum thickness needs to be recorded, and any substitutions have to be less than what has been passed. The density of the insulation is going to play a factor in what that heat calculation is, how much heat is generated when that material is burned. And again, that's peak heat release. That's also going to be flame and smoke propagation. Your minimum thicknesses are all going to be a consideration, not just from the NFPA standpoint, but also from your building code, thermal requirements of the building as well. So all these things need to be factored in. So if a weather resistant barrier is used over foam insulation, it can be used without foam. So in instances where you have open jointed panels, you need that weather resistive barrier behind the cladding. This allows you to omit insulation without actually having to redo the test. As mentioned earlier, the air gap makes a big difference in the overall performance of the assembly. So the tested air gap cannot be any larger in any substitutable type assemblies. So you'll see here the thermocouple is placed halfway through the air gap. Another thermocouple in the stud cavity, another thermocouple in the continuous installation. All these things are measured and strictly controlled. Your air gap really needs to be within a plus or minus half an inch. So, as mentioned earlier, brick as well as stone, non-combustible materials. You can certainly test with stone and stucco and everything else like that. You can test with the ACM panels. You can test with fiber cement. All these can be tested. EIFS is its own special category. And high pressure laminates, again, another special category. Typically, they're tested with only mineral wool or no insulation. You start using just a plastic insulation in there, and you just won't get a passing result. So the claddings are always going to be paired with an insulation if that's what the overall assembly calls for. And it will have the weather resistive barrier tested as well. When we talk window openings, you must use approved designs for these openings. This is going to be a significant failure point. This is what would introduce fire within the wall cavity between the potentially non-combustive exterior cladding and the combustible materials behind it. So this is really key, and there's no substitutions or alterations that can really be made to this if you do decide to substitute particular products. Polyiso and spray polyurethane foam may or may not require specific header and jamb details. EPS, GPS, XPS all require specific door window header and jamb details, and they must all be compliant with NFPA 285. Mineral wool, FR treated lumber, all these things can be used to create these header and jamb details. So after looking at these full assemblies, we now need to look at how can you look at weather resistive barriers and use engineering evaluations to include them in existing NFPA 285 systems. So worst case scenario is you have to test the entire wall assembly. These are very expensive tests. You're looking at a minimum of $25,000 US to test this assembly. And there are thousands of assemblies, so this can quickly spiral to millions of dollars in testing. So, as I mentioned earlier, what we're going to look at is, testing for the worst case that will still pass the initial assessment, and then any assembly that is less severe than the tested assembly that passed can be substituted by being reviewed by a fire engineer and issuing an engineering judgment based on the substitution to that initial assessment. And the whole idea behind this is there are tens of thousands of variants, and it's just not practical to be able to test everything. So when we get calls being asked, hey, does this product meet NFPA 285? The reality is, it depends. The answer is always it depends, because it depends on the entirety of the assembly. We cannot tell you one way or another whether one product is going to affect the entire assembly. But we can take an educated guess based on existing assemblies and have an engineer make that judgment. So these judgments by these engineers are done by assessing each layer. So if you can change one component, you have a pretty good idea of how that one change can affect the rest of the assembly. You can add a component. It can affect the results, but it also depends on the characteristics of that material. It depends on whether it is combustible, non-combustible. Sometimes adding a non-combustible material to an otherwise combustible product can improve those results. Removing a component can affect the results as well. So all of these things factor in. So you really need to start with an assembly that's going to closely match what you're trying to do so that you can make as few assumptions as possible in making a substitution. So first, you start with a tested weather resistive barrier as a baseline. Now that weather resistive barrier, is it less flammable than a tested weather resistive barrier can be to allow the replacement? Um, in order to determine whether products are going to be more or less flammable, we use a ASTM test called E1354, which is a cone calorimeter test. And this test is going to measure how quickly the product burns, how much heat is generated, peak heat release, average heat release, as well as the flame and smoke produced by it. So this data is going to be analyzed. It's going to be analyzed for how quickly it ignites, and as I mentioned, peak and total heat release. By comparing those results to an existing assembly that has been tested, you can make a judgment as to whether this is going to make the assembly better or worse. I mean, if you're within a % or two, the margin of error is quite small. It really wouldn't play a big factor. But if it has a higher peak release, a significantly higher peak release, then that would indicate that that assembly may not meet NFPA 285. That substitution wouldn't be acceptable to be made. So they do have a lot of information as far as what assemblies have been done, what tables and tables for various materials and how they perform. So each table is going to be typically specific to the installation brand. Now the brand does matter because there are chemical differences from one manufacturer to the next. So just a substitution from one manufacturer to another, even if it's the same installation type, doesn't mean it's going to have the same fire burning characteristics. So you need to make sure that you are looking at the right table for the right installation. So the test will tell you what alternates can be allowed. Each table is going to be unique. You can only use the components listed in the table. You can't jump to another table to find other components. You can't mix and match to get your best results. You really need to look at the table as a whole and pull your assembly based on that table. So all these details are from the NFPA 285 test report. So here's an example of the NFPA 285 table. And you'll see here, as we discussed, what is the base wall system. So it would be tested at steel stud wall with 5/8 inch type X gypsum. So you can substitute in your masonry wall, your concrete wall without a problem. What's your insulation? 1 or 2. What's your exterior sheathing? What's your water resistive barrier? And it will have a list of all the acceptable products that you can use. What's your exterior insulation? These are your choices. You have to be able to pick from that table. And then what's the exterior covering? And then it will list a whole assortment of various wall accessories. So as I said, you cannot mix what's in one table from an assembly from another table. So as I mentioned earlier, there's no such thing as an approved product. It's an approved assembly. You can't mix and match. The only people that can make a determination from those tables would be a fire engineer, and they would need the test data to support that claim. All right. The architect cannot pull this information from a spec sheet. It really needs to be done by a fire engineer. Contractors will always try to make substitutions. You need to limit your specification to what is acceptable within that tested assembly from the table that's provided. You must always follow the NFPA 285 tables. Even if you have all the materials right, the details do need to be done per those requirements as well. So to elaborate a little bit more here, your guide on NFPA 285 engineering evaluations or engineering judgments. They are working on a new guide being developed. It's based on a layer by layer analysis, and it will officially allow these engineering evaluations. It will allow any weather resistive barrier provided it is behind 2 inches minimum of non-combustible insulation. That's mineral fiber insulation, provided that insulation's met the ASTM 136 standard. And that's pretty much everything from the technical standpoint. I know this is a complicated subject, so I did leave a fair bit of time for questions. So I guess we can get started with those.
Sounds good. All right, let me remove. All right, thank you, Michael. That was really great. So yes, now's the time for questions. If you have any questions on this topic that you'd like to ask Michael, feel free to use that Q&A and drop them in there now. I did have a few questions come through. First one that quite a few people have asked is just would like to take away this presentation to share with other folks. Would you be willing to share the PowerPoint presentation?
Yeah, I should be able to convert it to PDF and share.
Okay, great. Well, you'll have the contact information of those people, so we'll get those out to folks. All right. Okay, so here we go. This person wants to know if you can provide vapor permeability ratings on your air barriers. They said, I'm working on a hot, humid climate zone and need to ensure proper vapor transmission through the wall assembly.
Yeah, yeah. So our products can range anywhere from approximately 30 perms up to 300 perms, depending on the application and depending on attachment method. So wide variation there. And that's based on dry cup. Wet cup, it's even higher. It would start at about 50 perms.
Okay, wonderful. Okay. With an ACM testing with a required engineering judgment, how much is the typical cost?
That's really up to the fire engineer, but typically it'd be in the neighborhood of $5,000 to $6,000 US to get an engineering judgment on a substitution. Again, your mileage may vary depending on which consultant you're using and the complexity of the case. So that's been our experience anyway. We have a few that we know and trust and have a long-standing relationship with. So we do use those.
Perfect. All right. How does the new guide for EEVs differ from pursuing EJs from a fire protection engineer, or will it just govern their review?
So the engineering evaluations aren't really official. These are people offering their opinion based on the changes. You got to understand that there's so many variations. You cannot possibly test everything, but they didn't have a mechanism in place to officially allow alternatives to tested assemblies. So, this is kind of quantifying what's already being done and officially making it as an acceptable means of acceptance. To my understanding anyway, and perhaps my colleague Peter can elaborate more on that if he's got anything to add.
Not at this point.
Okay, thank you. Sounds good. Next we have, are most designers using exterior insulation or cavity insulation?
It is entirely dependent on your climate zone and your thermal requirements. I'm in the Toronto area, so we're seeing continuous exterior insulation on just about everything. Um, Oftentimes, you just can't get enough thermal performance with exterior insulation, so they have moved more towards steel stud and cavity insulation as well. You get into more climate friendly zones or warmer, more temperate zones, you may be able to get away with just continuous exterior.
Thank you. All right, and now we have, if the insulation is combustible only on the top of the wall, but the rest of the wall components are non-combustible, is testing still required? Is there any percentage of combustible material allowed for assembly?
This kind of goes back to the very beginning. And again, it depends on the assembly. I believe if you're using any combustible insulation on the cladding side of the assembly, you have to have an NFPA 285. It's just a plastic insulation. It must be tested. Your exceptions do come into place with your weather resistive barrier. Again, that's only for buildings over 40 feet tall. And if it's behind a non-combustible insulation, then a NFPA 285 is just not required.
Okay, I actually think that is our last question. Well, thank you everyone for joining. Michael, if you don't have anything else, I think we're good to go.
Okay.
Everybody can go enjoy their weekend.
Appreciate that.
Thank you again, everybody from Dorken team. Appreciate the presentation.
Our contact information will be posted.
Yes, absolutely.
Okay, so if anybody is too shy to ask any questions or has any follow-up questions after the presentation, please feel free to drop us a line. We're happy to help you in your request.
Thank you so much. All right. Have a great day, everyone.
Thank you.
Bye-bye.